All right, so we've already talked about how to create basic 3D geometries and some of the methods you can use to kind of visualize them and project them onto your 2D screen. And this series is going to be Intro to Noise, which surprisingly is one of the most powerful tools you can use to make some unpredictable geometry and shapes, especially with texturing and space warping. It's the underlying tool for a lot of the interesting visuals you see, especially if you want to generate any kind of complexity procedurally in a pure mathematical way. So, in order to implement noise, we have to look at some ways that you can get some kind of randomness on a shader. Well, it should be clear that because we're running on a shader, all the pixels can be thought of being processed in parallel. On a typical CPU implementation, what you would do is to have some kind of a global state as the seed, and every time you query a random variable or a random number, you update a global number for the next query. So the classic one is XOR random number generator. However, we don't have the luxury here because we can't have some kind of global state that's being shared by all the pixels we're processing. So instead of what we're doing, instead of some kind of a randomness in that way, we can use, you know, we can use some kind of deterministic hashing method. In this case, since what we're doing is really given one input, we're giving a deterministic output, but it's just that the output is unpredictable from a human's perspective. When you look at the input, it's unpredictable what the output is going to be. And in this case, it's more accurate to call it a hash function. And turn out the hash function will be crucial to constructing a proper noise in a procedural way. So why don't we go ahead and take a look at that? Let's delete all the boilerplate code. So back to UV, resolution, sorry, it's for coordinate. This is just a normalization. If you don't know how this works, I suggest you to watch the intro series. And now let's write to a frag color, just this, and we set the RGB color to be the same value, so it's going to be monocolor. And I'm going to show you what hash looks like visually on a 2D screen. So hash UV, which is the coordinates. Remember, we're having a deterministic input and deterministic output. It's just that the result is unpredictable. And the alpha channel is going to be 1. It's not a big deal usually. And let's create our hash function, UV. Return some kind of value, return 0. And something's wrong with this apparently. Let's see. Oh yes, forgot to parentheses here. All right, so as you might have inferred from the title, there's one way you can implement hash that is not the best way, but it's the easiest to understand. It's called the sine wave hash. So here's a demonstration. So on the X component, put the sine wave. It's going to be something like this, and of course, you can kind of extend out the frequency more frequent, and you can see there's some dark parts, dark areas. For a value noise function or for a hash function that will be used to construct some kind of noise function, it is ideal to have the value it outputs to be clamped between 0 and 1. So I'm going to take the fract of the sine wave. It turned out it would be crucial. So the big idea is to kind of modulate the value by multiplying by some big number to the point that it's unrecognizable to be the original function, but still have a uniform distribution of the value. So this is basically kind of a hash function in one dimension. Right? In y-axis, you still kind of get to see the same thing. Well, a sine wave is a function that only takes one input. How can we make it take two inputs? Right? Well, there's a clever way to. This is kind of hashing. It's another smaller hash in the hash function. It's basically hashing, or so I'll have two-dimensional points UV here. We can hash it into a single value. There is a simple dot product. So seed can be dot UV. It's just some random number. You can tweak it to get even more. Another thing about this technique is that it is unreliable on different machines, on different if you drive your composites to different precisions, it produces different results, but it's the easiest one to construct. It's the most easily understood ones. But in the seed, right, you can see how the seed generates some kind of randomness in here. It's not perfect. Usually prime numbers work the best. Let's tweak some of the numbers in here as you tweak it. The randomness just kind of comes out. Again, depending on your precision levels, your floating implementations. And you can see if a full screen, there's still some kind of pattern emerging that way. So I'm going to tweak it. And that looks okay. What did I do? So still, you can see the problem with this method hashing is that it's really tweaky, and you can put some numbers in the frequency like I did before. And this time it looks okay-ish. The bigger this number gets, it's actually kind of the number that determines how random the distribution is. That's pretty random. It looks like some kind of static noise out of the thing. This multiplication can really be factored into the dot product, but you can see the kind of, it's just for tweaking purposes. So basically, let me explain kind of the significance of how do you tweak parameters. So you want the dot product to dot with a 2D vector of an XY component that's different values, because you want the hashing process on the X and Y component to be kind of independent, because if they're off the same number, then you can kind of see the pattern going to diagonally, because X and Z can be switched and the result could be the same, and therefore it manifests as a shape with the symmetry along the diagonal line going between X and Y axis. And if the value becomes too big, you can see it's flickering a little bit. That is part of part of the reason I say sine wave implementation are not the safest bet you can get, because reasons I don't know. Apparently it goes, because this kind of goes to a pretty big number and then gets fracted down, so there's some precision issues in there. Like sine waves can't really take really big values. Let me just show you. But if for an incredibly big number, you can see kind of there's a problem with it, right? You have to kind of control it. But if you control it in a reasonable range, it shouldn't be too bad. So there you go. That's a sine wave hash, which will be the underlying pseudo-random number generator will be used on a per pixel level, although a more accurate term will be hashing. So from now on, I'll refer to this process as hashing, and we'll build a kind of a simple noise implementation from now on. And then we'll kind of evolve from there into fractal noise, for node regions, different kind of noises, some of the interesting applications of noise. And from there, we can kind of go on to more produce more procedural images that have more complexity than the simpler geometries we've seen before. So hopefully you will like this.